Great. So first thing we're going to look at for vectors today is we're just going to define what it means for two vectors to be equal. It doesn't mean that they're drawn in the same spot. All right. So if you had something like, let's just take and put a grid there. Bless you. If you had a vector like that and a vector like that, they might be equal, right? If they're equal, it means if you put them on top of each other, you wouldn't even be able to tell the difference. So in that case, those vectors are equal. They both have different initial points. They both have different terminal points. But they still are the same vector. So saying two vectors are equal has nothing to do with where the vectors are. All it has to do with is, do the horizontal components match and do the vertical components match? So those two vectors are equal when exactly what I just said. The horizontal parts of the vector match, and so do the vertical parts. Right, so if I go back to the page that I just had, I'm going to draw slightly different vectors. But I'll just show you what I mean by the components. So let's have one here and here. So that's a vector. And here and here. Okay, so if those two vectors are equal, let's check the horizontals and the verticals. It's basically like you make a right triangle out of it. So this vector has a horizontal part of 2 and a vertical part of 1, 2, 3, 4, 5. Okay, so this would be the vector 2, 5. Right, now let's look at the other one. So this has a horizontal of 1, 2, 3, 4, 5, 6, and up 1, 2, 3. All right, so those two vectors are not equal. The horizontal components and the vertical components don't match. Any question on that idea? So it doesn't have anything to do with where they are. It's just do the components match. All right. So the last way we're going to learn how to represent vectors, and this is the most common way to represent a vector if you're not drawing it. Okay, it's called unit vector notation. So I said yesterday when we named vectors, we use a letter, okay, usually. Well, there's two special letters you can't use because think of those as like reserved parking spots. You just can't use those two because they already mean something else, right? It's kind of like when we do right triangle trig. We usually use Greek letters to represent the angles, like alpha, beta, gamma. Sometimes we use theta. But one Greek letter we would never use to represent an angle is pi. I mean, it's a Greek letter just like every other Greek letter I said, but the problem is in math, that Greek letter means something else. Right? Well, in vectors, the two letters I'm about to give you mean something special. One of the letters that we don't use because it's a special name is the vector I. It has nothing to do with complex number I at all. Totally separate thing. And the way you can tell that this is different, you might be like, well, wouldn't that be confusing? Because I can be a complex number, and now you're saying it's a vector. Well, it would be a bold I, or there would be a line on top of it. So you'd be able to tell the difference. So I is a special unit vector that always points one unit to the right. That's it. So I is a special unit vector that always points one unit to the right. Okay. And if you want to see a picture of it, that's what I looks like. That's it. There's one unit long and it points to the right. Okay. The next special vector is J. Okay. So the vector J, also a unit vector, but it points one unit up. And now the idea is that I and j are kind of like building blocks. You can stack them together to make vectors. And that's basically what we do. All right, so we're going to see how we can use I and j to build a vector by stacking as many i's and j's together as you need. All right, so here's a picture of j. It's 1 unit long, and it points up. Any question on what I and j look like? Now for 2D, you only need those two. Okay? This one can move me left and right. That one can move me up and down. There's no other direction I need to worry about moving in. So using just those two, I can move anywhere that I want. Now, I said left and right, or up and down. But this one only points right, and this one only points up. How do you think you would move left or down? What would you have to do to the I or j? Yeah.
Put a negative.
Yeah, if you have negative I, well, that would flip it around and it would go left. Negative j would go down. Okay. So let's see if we can write the vector 3, 4 using unit vector notation. Right, so when we're done, the unit's just going to have i's and j's in it. All right, so what I'm going to do, I'm just going to make these a different color. Because some of them are going to be right on top of the axis, and the axis is already black, so you wouldn't see it. All right, so we want to end up here. So we're going to stack as many i's and j's as we need to together to get to that point. Right, so let's start with the i's. How many i's do I need to put together, starting from the origin, to start getting towards the terminal point? Okay. 3. So I'm going to just take and make 3 copies of it. And I'm going to put 1, 2, 3. Now, I stacked them together exactly the way we would stack them the way I showed you yesterday. So what do you think this would be? That vector in red, if I drew the final answer, what would it be?
That is I3 or 3i.
3i, yep, that's how we say it. So we just stacked 3 of the i's together. All right, and now, Natalie, how many j's am I going to need starting from where I just finished up to that dot?
4.
Yep, I'm going to need 4. I mean, I could just draw it probably quicker than this, but... So we're taking 4 of those and putting them together. So 2, 3, and 4. Close enough. Okay. So now if you drew that vector out, what would that one be? The one that goes up. Yep. It would be 4j. And what operation did we just do with the vector 3i and 4j, the way that I've connected them? Yeah. Well, between the two vectors. So you've got, so basically right now you've got that, and you've got that. And what are we doing with those two vectors? Yeah, we're adding them together. We added them together. So you have 3 of the i's, 4 of the j's, and now if you connected from where you started, which is here, to where you stop, which is right there, that would be the vector 3, 4 with the angle brackets. So this is unit vector notation, what I circled. What you started with was called algebraic notation. Okay, any question on that? So we talked about what happens if you have to go left or right. You could just put a negative in front of the 3 or in front of the I or the j. You can also put fractions here, like if you had to go, what's that, like 6.5, 5.5. So you could do 5.5i. So you can get anywhere that you want on that plane just by combining i's and j's together. There's nowhere that you could put a dot that I wouldn't be able to get to, stacking i's and j's together. All right. And what the fancy word for that is, these two vectors, I and j, we say that they span two-dimensional space, which basically means you can travel wherever you need to. Now, let's say you got rid of j. You didn't have j anymore, so all you have is the unit vector I. Could you still travel wherever you want in two-dimensional space? Well, which way would you be able to travel now? If all you had was I. All you could do is travel horizontally. You could only travel in one dimension. Right? So, to come up with a set of vectors that span a space, like we just did here, I and j, you need as many vectors as you have dimensions. Okay? So when we get to 3D space, we're going to have to add one more. Okay? I, j, I'm going to add in k. Okay? Questions on that? Alright, so let's look at some formulas for vectors. So in the formulas that I'm about to give you, v and w are going to be vectors, and alpha is going to be a scalar. Can someone remind me again, what's the three things that can happen when you scale a vector? Rob?
It can get enlarged.
Yep, longer,
It can get smaller.
shorter.
And it can move, or negative, to get negative.
And what would the negative do to it?
Flip it 180.
Yeah, it's like it rotates at 180. So when we scale a vector, that's the three things that can happen. So we're going to go over everything we did yesterday, but now I'm going to show you how to do it without drawing. Okay, here's your two vectors. Vector v has a horizontal and a vertical component of x1 and y1 respectively. In vector w, it's got a horizontal component of x2 and a vertical of y2. If you want to add those vectors together, instead of drawing v and then taking w and connecting it onto the end and drawing the diagonal, all you really have to do, if you don't want to do it on a graph type method, just add the horizontal components together. So that's x1 and x2, comma, and then add the vertical components together, y1 and y2. So doing that arithmetic takes the place of all the sketching that we had to do to add vectors. Now, subtraction, that was one extra step. It wasn't really that much harder. All we had to do was take and think of it like this. We still think of it as addition, but we had to take the second vector, flip it around, and then add it. Well, if you just do arithmetic, it's a lot easier. All you have to do is subtract. But the order is important. V minus w means start with the v component and then subtract the w component. So the x1 or y1 is always first, and the x2 or y2 would always be second, in this case. Now, scaling a vector. That's where it can get longer, shorter, or change direction. So we can do it by drawing it. So if you had like that vector, and you wanted to know 3 times that vector, just stack 3 of them together. And that's your answer. Mine grouped together, kind of weird. But that would be your answer. So easy to stack them together and make them longer or shorter. Well, if you think of it, it's almost like a distributive property. Okay? If you want to scale vectors, all you have to do is take the number that you want to scale by and distribute it to each component. So take the horizontal component, multiply it by your scalar, then take the vertical component and multiply that by your scalar. And all these formulas work in 3D, all of them. You just have to extend the pattern that you already see to like z1 minus z2 or z1 plus z2. So 3D isn't really that much harder. And the last one is this symbol. Does anyone remember what the double bars around a vector means? These are bold. Yep. Yeah, it means magnitude. So if you've got a vector, like I kind of basically did it here. And you want to find the length of it. Does anyone remember what I said yesterday you would do? I mean, we didn't formally write down the formula, but it's a basic thing we've done a lot. Yeah? Yeah, you just do the Pythagorean theorem. So here's your horizontal component, square it. Here's your vertical component, square it. Add them up and take the square root. So when you see this formula, that's really just the Pythagorean theorem. Horizontal component squared, vertical component squared, add them up and take the square root. Now when you find a magnitude, magnitude is a distance. What kind of number should you always get for distance? Right? Yep, it's always a positive number. So yes, technically when you take a square root, there's always two answers, but you only go with the positive one because negative distance doesn't make sense. Okay. Questions on those formulas? All right, so now when we go through it and we write our answers, we're going to practice writing with the algebraic notation, and we're going to practice with IJ. Okay, you might be asked for either one. Okay, so here's your vectors, and I'm giving them to you in both formats. First one is unit vector. The second column is that's your algebraic notation. Okay. And remember, I don't want to do any of this visually, so you shouldn't be getting out graph paper and sketching any of this out now. Okay, so first thing I want to do is add V and W. Right, so Tori, if I add those up, what would be the horizontal component? 5. And if we write it as a unit vector, that would be 5i. So we got 5i. And Kaya, how about my vertical component?
Negative.
And what else would go with it? Yes, exactly. Now, when it's a negative 1j, you can just put minus j. That's fine. Okay, so there's your answer in unit vector form. Gabe, can you just change that over to me with the brackets?
So we got the open bracket and 5i. I mean, just 5.
Just 5, yeah.
Minus 1.
Minus 1. So when you write it with the open brackets, you don't need the letters, but you can't just leave the negative 1 blank. Like, you can't leave it like that. You can leave the negative 1 off in this case because you have the j there, so you got something to hold the place. But here you got to put it. All right, let's subtract them. Right, so this time we're doing v minus w. We learned yesterday that when you add vectors, it's commutative. So if you messed up the order you added them in, it doesn't really matter. But when you subtract them, you got to do v minus w. Okay. Let's start with that. So Emily, what would the, if we're going to write it in unit vector form, what's the horizontal part going to be?
It would be negative 1i.
Yep, negative 1i or just negative I. And Chris, what about the vertical part? Oh, is it too small? I made it a little smaller. So remember, what operation are we doing?
Addition.
So addition, that was A, but now we're doing B. Subtraction. So we got the horizontal, so negative I. What about if you subtract the j's?
Negative j.
Not quite. You gotta be careful on this one. If you just had 3 minus 4, I would agree with you, it's negative j, but this one's not 3 minus 4. It's 3 minus, Robin?
Since it's the positive 3j minus a negative 4j, you would add the 4j, so
Right.
it would be 7j.
Yep, so it's 3 minus negative 4j, which becomes plus. So exactly what Robin just said. Okay, so unit vector form. And Kathleen, can you give me that with the brackets? Negative 1, 7. So remember, it's kind of like you write a coordinate, but it's not a coordinate. It's a vector. Okay. So this has nothing to do with a location at all. Okay. All right. Let's look at this one. Okay, this one's a little different because for scaling, you don't need two vectors. If you want to add, you got to give me two things to add. If you want to subtract, I need two things to subtract. To scale, I only need one vector to scale, not two. So we want to do 3v. Right? So Nate, if I scale vector v by 3, what would I get?
You would get 6i plus 9j.
Yep. So you just distribute the scalar to each component. 6i plus 9j. Okay. Or Kaylee, if I want to write that with the angle brackets, what would that be?
6 and 9.
9. Yep. Okay, and the last one I want to find is magnitude. So this is another operation that you only need one vector. Okay, just v. I could have done w, but I didn't. Okay, so Ashley, if I want to find the magnitude of v, what's the first thing I should write down?
You do like the Pythagorean theorem. So
Yep.
You do 2 squared
Yep. So 2 squared.
plus 3 squared, and
Alright.
then take the square root.
2 squared plus 3 squared. Take the square root. And that's going to give me the square root of how much?
13.
13. Yeah. 9 plus 4. Perfect. 13. Just like always with square roots, if that came out to like square root of 20, you would want to reduce it as much as you could. But 13 is prime, so there's no reducing that. What's different about the answer that you got for D compared to every other answer? D's a different kind of thing. Yeah?
It's not set up like a coordinate. It's like the vector notation.
All right, so let me go back to the first thing you said. So she said it's not set up like a coordinate. So none of those are set up like coordinates, right? So now what's the second thing you said?
It's not in vector notation
Why isn't that in vector notation?
because it doesn't have a comma or the whatever those are called.
It doesn't have. Okay. Anyone else have a thought? Yeah.
It doesn't have a second answer, there's only one definite answer.
How come? Why doesn't it have two answers like all the other stuff? Yeah.
There's no I in.
Okay. So there's no I in J, which means D is what? Yeah.
It's magnitude.
It's a magnitude. That's not a vector. D is a number. Okay. A, B, and C are not numbers. Vector, 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 number. So it's a different kind of result. The answer is not a vector. That's why it's not written like a vector. Any question on that? All right, so reminder, if you have a vector that comes out exactly 1 unit long, that's called a unit vector. So what I want to do now is come up with a formula that will convert a vector into a unit vector if it's not. So there's two cases that could really happen. If it's not a unit vector, maybe it's too long, or maybe it's too short. Right? So I don't think we're really going to use the diagram. I don't think I need it. Let's say you had a vector. So the length of the vector came out to 5. If you wanted to make it a unit vector, what would you have to scale that by? Yeah? 1/5. So if you had a vector, you found the length, you said, okay, it's 5 units long. If you did a scalar product by 1/5, you would turn it into a unit vector. What if the length was 8? What would you scale it by now to make it a unit vector? Yeah? 1/8. Oops. 1/8. What if the length was a half? What would you have to scale that by to make it 1 unit long? 2. All right. So now, what about if the length was x? What would you scale that by to make it 1 unit long? Yeah? 1 over x. So that's the pattern. You always scale it by the reciprocal of its length. And if you do that, it'll always come out to 1. Okay? And that's what I have right below. Now, scaling it by the reciprocal is the same as dividing it by its length. So if you want to say, well, you would take x and multiply by 1 over x, sure. Or if you want to say, take x and divide by x, it's the same thing. So multiply by its reciprocal or just divide by its length means the same thing. So what we're actually doing is we're finding a new vector. We're not changing the direction. Still pointing the same way, because you're never going to scale by a negative. Okay? So it's always going to point the same way, but it's only going to be 1 unit long. Okay? And here is the formula. To find a unit vector, take your vector and divide by its magnitude. Or if you want to think of it the way someone said with reciprocal, that's fine too. Take your vector and multiply by the reciprocal of its length. Same thing. So first thing you always want to check is, see if your vector already is a unit vector. If they're asking you to make it a unit vector and it already is, then just say it already is. If it's not, then we'll fix it. Now, since finding the magnitude involves Pythagorean theorem, that means you're always going to be taking a square root. Sometimes you're going to get a nice answer for the magnitude, sometimes you won't. Okay. Depends on the numbers they give you. Okay, so I want to find the unit vector that corresponds to that one. So in other words, give me a vector that points exactly the same way, but is only 1 unit long, instead of however long this one is. So to find the unit vector, what do you think the first thing I should do with the vector in example 3? What should I do first? Wait.
Pythagorean theorem.
Yeah. Find the length of that vector and see what's going on. See how long that one is. So Blake, can you just set that up for me?
It would be 3 squared and plus 4 squared.
3 squared plus 4 squared. And if you do that out and take the square root, you're going to get a length of 5. Okay, so this is not it's not a unit vector. So what does that mean I need to scale this vector by? Robin? 1/5. So I'm going to take my vector and I'm going to scale it by 1/5, and that's going to give me a unit vector. Okay, so that's my goal, find the unit vector, which we just call u. Okay, so let's do it up. 1/5 of 3 - 4. So Madison, when I do that out, what's my horizontal component going to be?
Three over 5.
3/5. And what about my vertical component?
Negative 4 over 5.
Yep, -4/5. And that's it. That's how you find a unit vector. If they wanted it with the I and J notation, you could just do 3/5 I minus 4/5 J. Don't write plus -4/5 J. I mean, I know we kind of do that when we draw it, but you can just write minus 4/5 J. Okay, so any question on how to find unit vectors? Okay. Kind of the nice thing here, you can check that very easily. Square 3/5, and you get 9/25. Square -4/5, and you get 16/25. If you add them up, you get 25/25. And then take the square root of 25/25. Well, that's the square root of 1, which is 1. So you can check it if you want. Okay, so the last two things we're going to look at are word problems. Okay, the first one we're going to look at is a velocity vector problem. So what they usually give you in this kind of problem is an angle that an object is being thrown at and how hard, or I shouldn't say hard, how fast it's being thrown. And they're going to want you to turn that into a vector. Now, for our purposes, I know when you throw something, it starts to curve, right? If we try to take into account the curvature, that's going to get a little complicated. So what we're basically finding is like, if you were to throw this object in space, right, it would just keep going in a straight line. It would never curve back down towards something, as long as you weren't near a planet with gravity. So we're throwing it somewhere where there is no gravity. Okay. We've kind of taken into account gravity before when we've done projectile motion. That's not really what we're looking at right now. All right, so when you throw something, okay, if you throw it and the second it releases your hand, releases from your hand, it's going to go in a straight line because there's no gravity to pull it back down. It's just going to keep going. All right, so when we write vectors, we have a horizontal component and a vertical component. So you got to kind of split this vector up into its two parts. In order to split that vector up, what shape do you think I can draw out of the vector that's there? Yeah? A triangle. Okay, so we're going to make a triangle. What kind of triangle?
A right.
Yeah, we're going to make a right triangle. And the way we're going to do it, it's going to go like that. So now you've got the bottom side. Think of that as your horizontal component and the height. That's your vertical. And together, those two things combine to produce the path that the object is going to go in. The bottom one is going to think of that as like a force to the right. The other one is a force up. If something's pushing right and pulling up, you're going to end up going up and to the right. And it's kind of hard to see because I drew over it, but that's exactly the way the arrowhead's going, up and to the right. Now there's two things that they're going to tell you. One, they'll tell you the angle that you threw the object at. Okay, so it'll be at a certain angle. And the other thing they'll tell you is the speed that you threw it at that angle. Okay. All right, so let's, I want to make sure I use the same, yeah. All right, in the formula, I used alpha. If you want to keep it as theta, that's fine. It doesn't really matter what you call it. But in the formula I'm going to write down, I called it alpha instead of theta. Alright, so the idea is we gotta figure out this. Horizontal component plus vertical component. That's the formula we have to figure out. So basically, if you call the bottom side x and you call the height y, x would be a vector. Y is another vector. If you combine x and y together, that's the horizontal and the vertical. Okay? We just have to figure out what x and y are based on the angle you're throwing it at and the speed you're throwing it at. So let's start with the x. What side is x from the perspective of alpha? Yep.
Adjacent.
It's adjacent. Yep. And what side is the other side that I have labeled, that vector? That's the, yep, hypotenuse. So which trig function could I use that would involve adjacent and hypotenuse? Yeah, cosine. So let's figure this out. So the cosine of my angle equals. Now, you're going to fill in a number here and here. Right? So, what kind of numbers go in these spots? Like we just said adjacent over hypotenuse, but what about the adjacent? Like do you write how thick the adjacent side is? Do you write the color of the adjacent side? What about the adjacent side and what about the hypotenuse side? The length, right? So I said we were going to call the adjacent side x, but that's not the length of that side. That's the whole vector. So I want the length of this side. So what should I put in the bottom of that fraction? Yeah?
The square root of x squared plus y squared.
Okay, and that's going to give me, we can kind of, so you could do that, which is, it's really just the, what do you call that? It's the what? V. It's the length, but we have another name for it. Yep. It's the magnitude. Right? Okay? So that's your formula for cosine. It's the length of the adjacent side over the length of the hypotenuse. But remember, that was a vector, so we want the length of it. So we have to find that. If they don't give it to us, but they're usually going to give you that in the problem. The length of the vector is the speed you're throwing the ball at. Okay, now let's get x by itself. Multiply each side by the magnitude, and there is your formula for x. Okay, now what trig function would I use to find y? It's not going to be cosine because that's adjacent. Oh, Jacob,
Sorry, what's the question?
what trig function are we going to use for y?
Cosine?
So we already used cosine, so we got to use a different one.
Sine?
Sine. All right. Can you tell me what I would write down? But sine is correct.
I'm not sure on that.
Rob,
Y, because that's the opposite of the angle.
anything before we get to the other side?
Sine of the whatever that symbol is, I forget the name.
What is that symbol?
Alpha?
Alpha, yes.
Sine of alpha over equals y over the v with the vector v.
What about the vector v? Something specific about it. its magnitude. Yes. Okay, and now we'll do the same thing. Magnitude v. Multiply that to the other side times sine alpha equals y. Okay. So we fill that in, and that will basically give us our vector, or our formula. So there's two ways you can write it. You can write like this. Horizontal component, comma, vertical component. Or if you don't want to write it that way, you can write it with the I and the J. So it would be magnitude of V cosine alpha. And you put that number in front of the I, plus magnitude V sine alpha. And you could put that number in front of the J. Same formula, just two different ways to write it. So by writing it out using sine and cosine, you've broken the vector apart into its components, the horizontal and the vertical. And I think I write the same thing right there. All right. So if you're given the initial speed and the angle that you throw the object at, that's the formula you can use. Alpha is the angle you throw it at. The magnitude of the vector, that's the initial speed. Now, what I wrote here, if I go back to the other page, basically the same thing. Since I have the magnitude of V written twice, you can distribute it out if you want. And that's what I did right here. If you don't want to distribute it out and you want to leave it factored, that's fine too. Usually you're going to have to end up distributing it out in the problem. That's why I usually just write it this way. Okay, so any questions on the formula? All right, so let's take a look at an example. Okay. So it says you're throwing an object 50 miles an hour at an angle of 30 degrees. Find the velocity vector. And then I just want you to explain to me what you found. Like, explain what it means. Like, in terms of real life. We're going to get two numbers. I want to know what those two numbers would mean in real life. So let's start with the magnitude of our object. Emma, what's the magnitude of the object here? 50. Okay, so that's the speed that we're throwing it at. 50. Okay, and if you want to write it distributed, you can, because that's going to be my next step. Distribute all this 50 out. Okay, and Rachel, inside the parentheses, what's the first thing I'm going to put?
Oh, no, that would be cosine.
Cosine, yep. Cosine 30. And which component are we finding right now when we use cosine?
You're finding x.
Okay, so I had labeled it X in that diagram. So it's the, yep. It's the, the component that has the I. Okay, so we're going to put the I next. Which is the horizontal component. So that takes care of the horizontal. Plus, now we're going to do the vertical. Okay, anybody tell me what I'm going to write down for my vertical component? Yeah.
Sine 30j.
Yep. So all you're really doing is finding two sides of a triangle. That's all. finding the length of two sides. All right, so let's do that out. 50 cosine 30, make sure you're in degrees though. So 50 cosine 30 gives me 43.3 pi. And then 50 sine 30 is going to give me 25. And make sure you put the j with that. 25j. So there's the velocity vector that would represent throwing an object at 50 miles an hour at an angle of 30 degrees. So, question is, I want to know what these two numbers mean. What does the 43.3 actually mean? Yeah.
That would be the horizontal distance the object you drawn traveled. It's like that's your horizontal.
It is something horizontal, but it's not distance. But it is something horizontal. Anyone have another guess what that is? Yeah?
Like a horizontal force.
Which would translate to what when you're actually looking at the object? The force you put behind it translates into speed, how fast it's going. So that's the speed in the horizontal direction. So in other words, if you were standing right in front of this object and it was coming right at you, and you had a radar gun, and you pointed it right at the ball, and it's coming right at you, the radar gun would say it's coming at you at 43.3 miles an hour. If you're wondering why wouldn't it say it's coming at you at 50? Because for it to be saying 50, you would have had to throw them. Your radar gun would have to be pointed down at a 30-degree angle, and the ball would have to be coming up at the radar gun, right? But that's not what's happening. You're just pointing the radar gun straight at the ball, and it's arcing as it's coming towards you. So some of that speed is in the horizontal. The rest of the speed is in the vertical direction. What's a little tricky about the vertical speed is that's the vertical speed the second the ball leaves your hand. Like the millisecond it leaves your hand. But what happens to that vertical speed the whole time as it's traveling? What happens if you throw something up? What happens to it? Its vertical speed. Yeah? It slows down. Okay? In the absence of wind or any kind of resistance like that, horizontal speed never changes. Okay? Never changes. Because gravity doesn't affect anything moving horizontally. It only affects if something's moving up or down. So the second you leave your hand, the ball is traveling 25 miles an hour. So if you had a radar gun and you were like right above the ball and you pointed it straight down and you got the speed, like the second it left the person's hand, right, it would be going at that speed. But if you check it like maybe a second or two later, it's going to have slowed down. It's not going to be coming up as fast till it hits its highest point and then it comes back down. Okay, so that's the speed in each direction. Any question on that? All right. So, last problem. We're not doing the resultant force thing, so this is our last one. All right, so the last one has to do with what's called static equilibrium. Does anyone know what the word static means? It's static versus dynamic. Those two words are opposites. Yeah?
It doesn't change.
Doesn't change. Stable. It's not moving. Right? The objects on this table are kind of in a static situation. It's not dynamic. Things aren't swinging. Things aren't moving. And equilibrium means everything is balanced. Okay? It means basically that the forces acting on it are all balanced, so essentially it's not moving. Static equilibrium. Everything's balanced and nothing's moving. Now, when we're talking about static equilibrium, we're going to be thinking in kind of a two-dimensional world. So when we're thinking two-dimensionally, what directions do we have to think about movement in? Don't think 3D, just 2D, yeah? Left and right, and up and down, okay? So that means if things are balanced, the idea is going to be that the force pulling the object left and the force pulling the object right are the same. If they weren't the same, it would be swinging. Also, the force pulling something up is equal to the force pulling something down. That's the only forces that are balanced. Left and right equals up and down. We just have to figure out what these forces are. Okay, so that's the idea. We have two cables supporting a weight, but the cables are different lengths. If the cables were exactly the same length, then they would each have the same tension. That would be easier. But they're different lengths. Okay. The other thing is the cables are not perpendicular to the weight. So like the cables holding up the light are perpendicular. So if you assume a couple things, if you assume that all 5 cables holding up the light are exactly the same distance apart, and you assume that no part of the light is any heavier than any other part, then each cable is holding exactly the same amount of weight. And you basically could just say if the lights weigh 40 pounds, divide 40 by 5, and essentially that's what each cable is holding. That's easy, because they're perpendicular. But when it's at an angle, you have to make triangles and figure out the forces. So let's start with, let's call this cable, I'll label it T1 to represent the tension in cable 1, and we'll call this one T2. Now, what would happen if you were to take this cable and cut it? If you cut it and you can tell me what would happen, that's the way that the cable is pulling. Okay? Well, the opposite way, keeping it from doing whatever it is you're about to tell me. Yep.
The weight would swing to the right.
Yeah, it would swing to the right and which other way? A little bit.
Down.
It would fall down a little bit. So this cable is pulling up and to the left because it's keeping it from swinging down and to the right. And the same thing here. If you were to cut that cable right there, all of a sudden this weight would swing down and to the left. So this cable is pulling up and to the right. Questions on that? All right. So now what I want to do is just put in some horizontals and verticals to kind of make some triangles. I'm going to put in a horizontal right about, that's bigger than I need, but that's okay. So there's a horizontal. And let's put in a couple verticals. Those are probably bigger than I need, but that's okay. Right. So now what I'm going to do is visually I'm going to break these vectors down into their components, and then I'm going to do it with right triangle trig in them to get actual numbers. Okay. So let's call this component x1. That's the horizontal component for cable 1. Let's call this x2. I'll just put it up here. That's the horizontal component for cable 2. I'm going to call that one y1. That's the vertical component for cable 1. And that's y2. So if you combine x1 and y1, you get a force that's pulling left and up, and that's exactly what the cable in black is doing. If you combine x2 and y2, you get a force that's pulling right and up, and that's what cable 2 is doing. Any questions on that? All right. So now I'm just going to make those right angles. You probably already do. All right, so let's kind of fill this in. We're not even going to have to use sine and cosine yet. I'm just going to use labels x1, x2, y1, and y2. And the 1,200 pounds, because that's important too. Okay, what's the force the only force in that diagram that's pulling straight to the left? Yep. X1. So in first equation, we've got X1 equals force pulling right. What's the force that's pulling right? X2. We have to figure out what those are using sine and cosine and the angles, and we can figure out some other angles based on the two that we have. So there's your first equation. Second equation. Force up equals force down. Which forces are acting up in this diagram? Yeah. Y1 and Y2, and they're working together, right? Because if you cut one of the cables, the weight wouldn't fall to the ground. It would still be held up by the other one. So Y1 and Y2 are working together to hold up what's trying to pull down. What's trying to pull down? Yeah. And how much is that? So whatever that is, yeah, it's 1,200 pounds. Okay. So as far as kind of the physics part, like you've set up the equations. You've said that your forces left and right are equal, your forces up and down are equal. Now you have to use trig to replace x1, x2, y1, and y2 with sine and cosine. And then we can solve it. But any questions setting up those equations? Okay, the rest of it gets kind of repetitive with the trig. All right, so we can fill in some of these angles. That's a 30. There's a lot of ways you could figure out that's a 30 if you think of these as two parallel lines cut by a transversal, alternate interior angles match. Or you could just say all the angles in a triangle add up to 180 and that one has to be 60, so whichever way you want to do it. And this angle down here is 45 for the same reason. All right. Now, could you use this angle up here? Sure. You could use that one, or you could have used this one. It doesn't really make a difference. I didn't. Okay, let's start with x1. We want to come up with a formula for x1. We want to use that angle, and the hypotenuse, I've just called it t1. Okay, that's the hypotenuse. If you want to put it here to remember it, you can, but I thought there's kind of too much going on, so I tried to move it away a little bit. But that's T1. And that's T2. So X1 is which side? Opposite, adjacent, or hypotenuse? Okay. Adjacent. And what about T1? Opposite or hypotenuse?
Hypotenuse.
Hypotenuse. Adjacent, hypotenuse. Which trig function is that? Oh, right?
Sine or tangent.
Tangent is opposite over adjacent.
Okay. Cosine.
Cosine. Cosine is adjacent over hypotenuse. So let's set this up. Cosine of Madison. What's my angle I'm using?
30.
Yep. Cosine 30 equals adjacent over hypotenuse. X1 over T1. And now we want to get X1 by itself, so we have something to plug in for it. So what is X1? Yeah.
T1 cosine 30.
Yeah. They're all going to look something like that. Like T1 cosine 30, T1 sine 30, T2 cosine 45, T2 sine 45. All the horizontal forces always use cosine, all the vertical forces always use sine, and you'll always have the T1 or T2 in front. Let's do one more. We'll set that one up. And then the rest of them we can probably just figure out by the pattern. So now I want to find y1. Blake, what side is y1?
Opposite.
Opposite. And t1 we just said? And which trig function has opposite and hypotenuse? Sine. So we're going to set it up just like we did, except sine 30 equals opposite over hypotenuse, y1 over t1. What's y1 going to equal? Yep.
T1 sine.
Yeah. Now, let's just see if we can figure out x2 and y2 without setting it up like that every time. You can if you need to, but just look at the pattern. So, x2. Well, it's the hypotenuse times the cosine of the angle. The vertical is always the hypotenuse times the sine of the angle. If you don't want to follow that pattern, don't. Just do it from scratch. But let's see if we can figure it out. So, in the triangle on the right, what's my hypotenuse? Yep, T2. And what's the angle that I'm using? 45. So one of them is going to be T2 cosine 45. The other one's going to be T2 sine 45. Let's look at which one's which. The x has the cosine. So T2 cosine 45. The other one, T2 sine 45. Now, we've done the physics part. We set up left and right equals, up and down equals. We've done the right triangle trig, so the trigonometry part is done. Now this is going to turn into a system of equations. So now it's like Algebra 1, solve the system. It's not nice numbers. It's going to be all decimals, but the calculator doesn't care if it's decimals. So we just use a calculator. So let's set it up. x1 equals x2. T1 cosine 30 equals x2. T2 cosine 45. Okay, that's my first equation. Second equation. y1 plus y2. T1 sine 30 plus T2 sine 45 equals 1,200 pounds. And now you've got two equations. They each have two unknowns in them. The tension in cable 1, the tension in cable 2. Easiest way to do this is to use substitution. So which equation would it be easier to get something by itself? Top or bottom? Yeah.
The top.
Yeah, I think the top, because you just have to do one thing. Can you tell me one thing you could do to get either T1 or T2 by itself?
Divide the right side, or both sides, by cosine 30.
Sure, divide both sides by cosine 30. All right, so I'm just going to put an x next to that because we're not going to use it anymore. We're going to do what Nate just said. So T1 equals T2 cosine 45 over cosine 30. I'm going to use that one, and I'm going to use that one. All right, at some point I need to round these off. Okay, so I think this is a good time to start finding these decimals. So let's do that one first. Cosine 45 divided by cosine 30. That's 0.816. So T1 equals 0.816 T2. All right. So we got that. And let's take the other equation and change that to decimals. So now we're going to have, let's see, sine 30 is 0.5. So 0.5 T1 plus, I know sine 45 is 0.707 T2 equals 1,200. Now, what would I do with that?
Can you substitute the T1 in for the T1 in the other equation?
Substitute that in. So you're going to have 0.5 times 0.816, which I'll do that out in a second, plus 0.707 T2 equals 1200. So again, the numbers are awful, but I'm not worried about doing it by hand. 0.5 times 0.816. It's 0.408. So 0.408 T2 plus 0.707 T2 equals 1200. Now, what can I do on the left-hand side?
Add like 3.
Yep, combine like terms. 0.408 plus 0.707 gives me 1.115. And last step to get T2 by itself. Yeah, Chris?
Divide 1200 by 1.115.
Yep. Divide by 1.115. 1.115. So the tension in cable 2 is 1200 divided by 1.115. 1076. Let's just say 1076. So tension in cable 2 is 1076. Tension in cable 1 is that number times 0.816. So take that number times 0.816. So 1076 times 0.816. It's about 878. So it's not an overly short problem. It gets very repetitive if you do a lot of them because they're all exactly the same. But that's how you do it. Okay, so as long as you know right triangle trig, I think you're pretty good. That's the hardest part. All right, so the homework, again, it's in the packet. That's not in your book. You don't have to worry about 64 or 69. Okay, so it's 25 to 47 odd, 55, 57, and 66. Don't forget 66. It's just kind of hanging out there by itself now. So 66. You know what? You can't read 66 because the weight of the box is photocopied all black. So, oh no, it says it up above. It's 800 pounds. So if you actually read the problem and you don't just look at the picture, it says 800 pounds. You should be okay. All right, so we'll take a look at that tomorrow.